All right, in this lesson then, we're going to apply the complementary filter to our accelerometer and gyroscope data, right? We've seen that the accelerometer is a good indicator of angle orientation only when it's static, right? When it's not moving using the gravity vector. So of course that doesn't help us on a moving robot. We need something that's a good indicator in dynamic conditions. And that happens to be the gyroscope. We just took a look at that in lesson 10. But we also saw with the gyroscope then that we have a problem of drift, right? Over time, there's this DC offset hour error that gets integrated right, into our measurement. And it then what drift means is if we start in one position, we move around and we come back to the same position, that drift error will say it will not give us the same position, right? It will be off. So we want to be able to try and get rid of some of that drift error, and we want to take the best of both, the best of the accelerometer, which over the longer term gives us a more stable, gives us a stable acceleration vector in terms of where we are angle-wise. That's a really lousy explanation of that. All right, the accelerometer over the long term will give us a good measurement of our angle if we can filter out the effects of any vibration. And we've seen with the accelerometer that if we use something like a low pass filter on it, then we can get rid of some of that high noise. With the gyroscope, right, the gyroscope works best in a dynamic condition, right? It's constantly changing. It's a higher frequency change. So the gyroscope needs basically a high pass filter with it. So what a complementary filter does is it takes the best of both worlds. Complementary filter uses two filters that complement each other. So if you think about it then, a low pass filter and a high pass filter are complements of each other, right? Because we know the low pass filter then only allows signals that are less than its corner frequency basically to pass, and a high pass filter doesn't pass signals that are lower than its corner frequency, only higher, right? And so what this signal flow diagram is saying is if we feed then the accelerometer angle in through a low pass filter, and we feed the gyro rate, if we integrate that over the sample time so that we can get the angle from the gyro, right, run that through a high pass filter, sum these two together, in effect, we're passing both frequencies, both signals, but we're cleaning them up, right? And so it complements each other. So we're going to see that this alpha, this weighting factor that we use here, which is very familiar from the low pass filter that we've taken a look at, is going to weight how much we say and how much we trust one signal over another over the short term, right? So here's the general form then, right? We say that the output of the filter, theta n, is equal to this alpha, the scaling factor, times theta. So the angle, the filtered angle output that we had at the time before, the sample before, we're going to add to that the gyro rate. So this theta dot gyro is the gyro rate we just read times the sample time interval. So there's that integration step, right? We get degrees per second times seconds. This gives us degrees, so units of degrees here. We're going to add to that, right? Well, 1 minus alpha. And so these values, alpha plus 1 minus alpha, have to sum to 1, right? So alpha is always going to be something less than or equal to 1, right? And greater than or equal to 0. All right, so 1 minus alpha times the reading that we get from the accelerometer in the sample interval. So that's our general form of our complementary filter, right? And we want to take a look at then, if we look at this equation and we say, well, how is that a low pass and how is that a high pass filter? How is that doing it? Right. So what we want to do is, if we look at this formula and we're going to assume the gyroscope reading is 0, right? So if the gyroscope reading is 0, that means we're in a steady state, right? We've only got the accelerometer data coming in from the formula, right? Because if we zero this out, right, what we have here is we have alpha times the angle, the filtered angle output from the time before, the sample before. So notice the gyro data is 0. That's why that term is missing. Plus 1 minus alpha times the accelerometer data. And if you look at this form, this is the very same form that we've used for a low pass filter that we've previously studied, right? That form that we looked at is we said, well, the output Y was multiplied by the current input x. So x were the input values. So think of this as the accelerometer input times 1 minus alpha. There's that term. And then what we added to that before was the previous filtered output. There's the previous filtered output times alpha. That's how this acts as a low pass filter, is if we think of the gyro as being 0. If we take out the effect of gyro from that, we can see that that is low pass filtering then this portion of the accelerometer angle. This walks through as well if you wanted to convert then this equation to its Z transform, right? This is what this is doing. It's taking this equation. So here's the same thing down here. And if we want to put it in the Z domain, right, we know that the n minus 1 becomes the Z minus 1 term. We pull that out. So we actually then have this in the form of theta, right? It sample Z is alpha times Z minus 1 times theta Z plus 1 minus alpha times the theta from the accelerometer, right, at time Z. Right? And then I'm pulling out then both of these theta terms. So we're moving this to the other side of the equation here. So we have both of the filtered output terms on this side, right? We have the accelerometer on this side. And so we want to put this in the form of a transfer function. Then the output, right, over the input, that relationship here becomes 1 minus alpha over 1 minus alpha, right, at the scale, or 1 minus alpha times, right, that time delay, right? That's the previous sample, right? So that Z minus 1, that's your time delay. All right. And if you then also want to relate this to the time constant that we talked about before with the low pass filter, right? The time constant, that should be tau. This shows as t. Approximately equals this formula. It's not exact, but it's close enough. So if you want to calculate alpha based on what you want your time constant to be, right, here's your formula that you use. Alpha times delta t divided by 1 minus alpha, where delta t is your sampling period, right? And then if we want to think about how does the time constant tau relate to noise, well, the easiest way is to think of it as an example. So suppose our sampling frequency was 100 hertz. 100 times a second we read this. That means our sampling period is 10 milliseconds. If we set alpha equal to 0.8, our time constant is 40 milliseconds, right? Plugging things into this formula. What that means is that any noise that is shorter in duration than 40 milliseconds will be removed. So that's how we can think about the time constant in terms of how we're sampling this and how often we're sampling this. In practice, what you're going to find is that alpha a lot of times is 0.9 or higher because the gyroscope will be giving us good information. Actually, for this particular filter, you might find that 0.96 to 0.98 works fairly well for alpha, right? Because the gyroscope will give us the best measurement in the short term. Right? The other thing is then how does it act as a high pass filter? Well, we start with that original equation, right? And we're going to remove the accelerometer signal from that, right? Assume that the accelerometer signal is zeroed at that point. We're going to leave only the effect of the gyroscope signal. So our formula reduces to this, right? Our filtered output is equal to alpha times the previous filtered output plus the gyro rate, the current gyro rate times the sample time. Right? And if you look at the general form of a high pass filter, well, I'm using i's here instead of n. Y of I is equal to alpha times, so y is the output, so the filtered output is equal to the alpha times the previous filtered output, alpha times the previous filtered output, plus alpha times the change in input values. Well, here's alpha times the change in input values, right? That theta dot, that's our change from the previous time. So this then does act as a high pass filter. Like I just said before, alpha values are usually large because we want the gyro to have a short-term effect on the angle estimation. The smaller weight on the accelerometer actually then has a longer-term effect of getting rid of the drift, right? Getting rid of some of that, any of that noise that might be in there from the DC offset. If you look at the lesson 10 video, after I moved my unit around, my MPU 6050, and we let it sit for a while, we could see that at first the drift was large, and then the drift was getting smaller and smaller as it just sat there statically. Of course, your robot can't just sit there forever and hope that the drift will come back, but what you're going to see in your homework assignment, hopefully, is you're going to implement now the complementary filter, right? You're going to compare that against what you're getting out of the accelerometer, what you're getting out of the gyroscope, and see which gives you the best results. Hopefully the complementary filter will do that. There are some other filters that are more complex to implement. Remember, we're running this on an Arduino microcontroller, so we want something quick and dirty, not a whole lot of math, right? We need our code to fly across that microcontroller. If we implement something, say like a Kalman filter, it's a little more complex to understand, right? We'll talk about it later in the course, but for right now, this filter should do really well for our IMU. All right. So I will see everybody in the next unit. I believe this is the end of our unit on the IMU, right? We're going to start moving on to motors, control systems, obstacle detection after this.